To finish the study of the cell phone, now we are going to consider the downlink. That means when you are receiving the signal from a nearby base station. Okay? And we are going to change a little bit the parameters and the situation just to see more examples. Now, this is the base station, and let's assume that you are in a large city and you are indoors, which happens quite often now. And this is a speech connection, and this is a data connection at 144 kilobits. Again, indoors, but now you are in a suburban area. So you are just talking and receiving data. Once again, we start with the transmitter. Now it's the base station, before it was the mobile. And here we have the transmitted power. This is the 20 watts power that is available on the base station transmitter, but this has to be shared by many different channels. So let's assume that for that connection, the base station is just using 3 watts of power. That's 35 dBm. It could be different depending on the channel, depending on the situation, on the traffic, but let's take this value. Then we have the base station antenna and cable losses. So we apply those numbers, and at the end, we find the equivalent isotropically radiated power by the base station, that is 50 dBm. That's equivalent to 100 watts, roughly. Now, the receiver now is the mobile, and the mobile has a bandwidth of 3.84 megahertz. We do the same thing. The noise figure of the receiver is worse than the transmitter. In general, this is true. And let's be under the same conditions. The antenna noise temperature is the same as the reference temperature, so we just find the noise. We cannot add interference margin here because this is really very changing and it's very complicated. So let's forget about the margin now, and we'll consider afterwards the need of this margin. So now we have the noise level here. This is our noise floor, in this case, no interference considered. And with this number, now we go to the phone when it receives. This is the data rate for speech and data. This is the code, so the spreading code, 3.84 megachips. This is the processing gain, in both cases, the required signal-to-noise ratio. We've seen this before. And we find the receiver sensitivity. Now we go to the receiver, and here we have no gain in the antenna. For the speech, we have a loss of 3 dB due to our body. We take a fast fading margin of 4 dB and a slow fading margin, but also of 7 and also a gain of 4 dB. But we have something new here. We are inside the building, so the signal is not going to penetrate easily inside the building, inside the room. This depends if you are close to the window, depends on the orientation of your house, depends on many things. But let's take a typical value of 20 dB loss. That means that only 1% of the signal will get into your room. If you go out, then the signal will be really 100 times higher. And with this, you find, once again, the maximum allowed path. All right? And those are the numbers for this case. And this gives you the maximum allowed path in the downlink. But the problem here is not the downlink in those connections. The problem here is the uplink. Okay? So the interface normally is considered after studying the uplink. I'm not going to repeat the calculations. I only give you here the parameters for the uplink. So for those two situations, here you can track the parameters for the uplink, okay? Plus the margins. And once again, the antenna noise temperature is the reference temperature. With this, we work with the previous expression. We see the maximum allowed path loss for the uplink. And look at the numbers. This is the limiting factor. So we are limiting our connections by the uplink. So, if now you want to consider the interference margin, you are free to do it, but you know that as long as you don't exceed the difference of those two values, 15 dBs, things are going to work. If you have an interference margin that is worse than that, then you are in trouble. But if this is the margin, in both cases 15 dBs, then there is no need to be worried about. So that's the way to deal with interference in the downlink. You always compare and find the margin from the uplink, that is the one that is limiting. And see the limiting number here. For the same parameters as before, this is the expression for the metropolitan and the suburban case. And this model that is limited by the uplink will tell you that if you are well indoors and trying to communicate, for a speech connection, maybe half a kilometer is going to be the far away that you can be from the base station, and for the data connection could be close to 1 kilometer. So if you are far away and your distance to the base station is larger than this, then there's only one way you can communicate. It's going outdoors instead of being indoors. But today we give for granted that cell phones should work very well in an indoors environment, and that may be not true. It will depend on the base stations, how they are distributed, and how close you are to the base station. Now we are talking about 3G, but now in the market, operators talk about 4G. 4G today is still a marketing name. The technical process is still ongoing and is called LTE, long-term evolution. And they are redefining the architecture for the new generation of phones. And there are important changes. One is going to be based on an Internet Protocol architecture, an IP network architecture. They are going to use only pack switch connections. They will forget about circuit connections as before. They will be using turbo coding for the transport data. And also they are changing the access. You have seen frequency, time, codes, and now there's going to be a different set of access process. They are called orthogonal frequency division multiple access. And this is the one that is being used, for instance, now in digital terrestrial TV. They're going to do duplexing both in frequency and time domains. They could have carrier bandwidth from 1 to 20 megahertz and high-level modulations up to 64 QAM. They are going to support a larger number of active data clients. And now, if you use sets of combined different antennas, MIMO antennas, which are different multiple input and multiple output antennas, and a 20 megahertz bandwidth, that means if you are the only guy connected to that network, then you may have bit rates up to 74 megabits in the uplink and 300 in the downlink. But this is totally science fiction, because you will never be the only user there, and the base station is going to control the data is being sent in to you. But you will have a very low latency of less than 5 milliseconds, and it is going to support very different size. And there's one important change. They are going to increase the speed at which the trains, especially the trains, could be connected to those base stations. It should be also compatible with the previous system as normally is needed. And this is what will be next in the future, but then you are going to see later on 5, 6Gs and whatever. It's going to keep going on. And to finish with the cell phone, this is just the credit and the acknowledgement to the people that have participated in this video recording and preparing the material.